Thank you, Boyan and Sirakov, for accepting give a talk in our virtual meeting in PDEs and applications. Boyan Sirakov is from Pontifícia Universidade Católica do Rio de Janeiro, Brazil, and he will talk about a Liouville-type theorem for the Lane-Emden equation in a half space. Please, Boyan.
Thank you very much, and congratulations for the very, very nice initiative to organize this meeting, and of course, a lot of thanks for inviting me to it. So what I'm going to talk today is a very recent work with Louis Dupain and Philippe Souplet from respectively Amiens and Paris in France. And it's on a new result for non-existence of a positive solution of the very standard equation, the Lane-Emden one, in half spaces. So let's move to the presentation. So to start with, okay, let's just, Liouville means, as for a standard, the classical result by Liouville himself, you say that a non-negative solution of elliptic PDE in an unbounded domain is constant. That's for, of course, the original result was from for harmonic or superharmonic functions. And okay, nowadays we care a lot about nonlinear equations, and probably the most standard, the canonical example of these equations is the Lane-Emden equation, which is the proportion of u to the p for p bigger than 1. And well, a result, probably the most famous result that I'm going to quote about Liouville theorem. So Liouville theorem for that equation would be there are no positive solutions, or if a non-negative solution is, if you have a non-negative solution, then it is 0. Well, the really most famous, the big daddy of Liouville theorems for any sort of nonlinear elliptic PDE is the theorem by Giddens and Sprack from 1981 that tells you exactly for which P's this equation has or doesn't have solutions. And the result reads, as probably everybody knows, that for P smaller than the critical exponent n plus 2 over n minus 2, there are no positive solutions of this equation in Rn, and respectively, they are non-trivial solutions for P bigger than this exponent. Okay, so of course, ever since that point, the question that has been in fact open is how about the Dirichlet problem in other unbounded domains? I mean, there are no, even up to today, there are no full results of this sort for other unbounded domains. So in particular, the simplest unbounded domain one can think of after Rn is the half space. So that's the question we are looking at today. And well, so we have take Rn plus to be a half space given by the xn variable, and look at that equation with a Dirichlet boundary condition on the boundary. And well, this has various motivations. I mean, to start with, and this really is sufficient as a motivation, is simply that it is, in a sense, the simplest unbounded domain. It's just like if you think of a basic PDE course, the first thing you study is how to solve the Poisson equation in Rn using the fundamental solution, and then you pass to the green function for the half space. This is really like the next step after the half space. You just want to solve it in that simple unbounded domain, which is in a sense not so simple because it also has unbounded the boundary. And also studying this problem has various other motivations, because through rescaling, you get a priori estimates for pretty general equations in bounded domains. And this also gives existence via degree theory. This also has been known since 1981, and an important work by Giddens and Sprack. In that work, actually, they established similar, but not exactly the same result for the half space. So they proved that for P smaller or equal than the non-trivial than the critical exponent, there are no positive solutions of the problem in a half space, for the Lane-Emden equation in a half space, which combined with their previous theorem is sufficient to run this program about a priori estimates and existence through rescaling. So Well, but already here one sees that there's something different happening, because they prove that for P equal in particular, there is smaller or equal here. For P equal in particular, still there are no solutions. One in Rn, there are for P equal. So that already showed that something different is happening in the half space. And it's been actually a question that's been going on for 40 years, and it's not still completely settled. What's happening beyond the critical exponent for the Lane-Emden equation in the half space? Even that simple thing is still not completely settled. We have some contribution to it. So let me run through the bibliography. I mean the main results on the Lane-Emden equation in particular. Okay, to start with. Okay, so beyond the critical exponents n plus 2 over n minus 2, there have been only results for bounded solutions, actually. And where this comes from, that's in some very general, the very general and basic reason for that is that if you have a bounded solution, you have a priori compactness. I mean, no matter by regularity, I mean, bounded solution implies a C1 or C2 bound, and then whenever in any bounded domain. So this means, for instance, wherever you put a bow in your with radius 1 in your half space, you have the same regularity estimates there if your solution is uniformly bounded in the whole half space. So that's probably the principal reason for which bounded solutions have been, in a sense, simpler to study. But this is even not that simple for bounded solutions. So about 10 years after Giddens and Sprague, Dancer, in an important work, proved that the critical exponent can be taken up to n plus 1 over n minus 3. And how did this happen? Well, he observed, of course, that's not so, he observed that by moving planes, one can show that bounded solution is also monotone in the normal direction, monotone in the xn variable, increasing, that is to say, a positive bounded solution. This is done by a clever application of the moving planes method. And then, since it is bounded, when xn goes to infinity, it converges to a solution in Rn minus 1. And then the Sprague result in Rn minus 1, that is n plus 2 over n minus 2 with n substituted by n minus 1, which gives exactly this exponent, applies. Okay, about 15 years later, Alberto Farina found a way to relate the theory, actually this Liouville result, to theory of stability of solutions, the theory of stable solutions. And through stability, since monotone in xn implies that the solution is stable, because the derivative in xn, which is now a positive solution, is a solution of the linearized equation. And therefore, any monotone in xn solution is stable. And so through stability estimates, he showed that for p smaller than this exponent here, which is a little bit scary, but for people who work in stability, it's not something new. Well, you have the non-existence for bounded solutions. So let me show you that actually anytime a denominator here is 0 or negative, this means that this dimension is covered. So the Dancer's result covers dimensions up to 3, and Farina has no restrictions for dimensions up to 11. And a couple of years later, through a completely different method, very clever observation by Chen Li and Zhu, actually, it was even a bit surprising. They show that there is no restriction in P for bounded solutions. Simply, there are no solution for any P up to infinity. And they found a way, and I'm gonna describe that since we're gonna use it too. They find a way to observe that if a function is a bounded solution, then it is convex in Xn. Okay, then obviously this is contradiction per se. A bounded function cannot really be convex if it's not a constant. So you prove that from bounded you have convex, but then this means it's a constant since it's positive. So these are the state of the matters. And okay, so what we prove here in a paper that we posted just a few months ago with Louis Dupin and Philippe Souplet, is that we can rule out any monotone solution precisely without assumption of boundedness. This is sort of a conjecture that's been done a number of times, in particular by Norman Dancer in a meeting I attended in 2009 in Oberwolfach on Liouville solutions. Is that this is what essentially is being hoped for, that if it should be possible to exclude that monotone solution should exist. I recall that bounded solutions are necessarily monotone by moving planes, but the monotonicity in itself should be sufficient, and that's what we prove. And the consequence of that is actually we exclude any solution which is bounded on finite strips, which means for each sigma r in this form, there is a bound on U, but of course, depending on R, it can grow up in R, but still that's enough to rule out solutions. Okay, that's the fact that bounded on each finite strip implies monotone is essentially flows from the methods of Beresticki, Caffarelli, and Nirenberg for studying moving planes in unbounded domains. The full proof is written actually in a paper by Alex Quas and myself in 2006. We wrote it with the assumption of boundedness, but what we prove precisely in what is contained in the proof is that bounded on a strip is sufficient for monotonicity, bounded on each finite strip. So essentially, we have to prove that monotone solutions do not exist. And of course, at this point, the big open problem continues to be: are there solutions which are not monotone? Which of course now should be should be very weird, because they should blow up at finite distance from the boundary, and somehow they should blow up in the tangential direction, and they are not even authorized to be in monotone. And this is a very weird profile. So this doesn't look likely, but we do not know at this point how to exclude it. The full result is still not achieved, even though that's okay. And added bonus of the method is that we can actually consider any nonlinearity f of u instead of u to the p, provided this f of u is a convex function. So that's my next slide here. A general Lane-Emden in a half space is taken f of u, and which is convex with 0 and 0 in positive function, then we have the same result. I mean, there are no solutions which are monotone in Xn or which are bounded or each finite strip. That's the same result actually. U to the p is of course such a function. So a couple of remarks about this hypothesis, f of 0 to equal to 0. If f of 0 is strictly positive, we can actually classify all non-negative solutions for convex functions, and even in much more general settings. If time permits, I'll come back to that. But this is by much more standard method, actually. It's uses essentially known results. And if f of 0 is negative, then of course this is a completely different problem. F is not a positive function. That's a totally different thing. Okay. So this is the picture of existence in Rn that we have at this point. Right. So let me move to. So let me now going to explain a little bit about the proof of that this result. That's on this slide. Well, to start with, I mean, we are going to use the same idea of Chen-Li and Zhu, which was that we are going to show that if a monotone in the normal direction function exists, then it should be convex. And we are going to exclude convex solutions. That's not very difficult. But the way to prove it's convex, if you don't have boundedness a priori of the solution, is very different. So let me move to the proof. First, let me explain that the first thing we're going to observe, it is not a complicated thing in our setting, is that there are L1 bounds for even in a much more general setting. I mean, just a function which grows at infinity at least is linear is such that any positive super solution of the problem in a sufficiently big ball, if you can go sufficiently far from the boundary, is uniformly bounded in L1. That's very standard. Just multiply, just test the equation with the first eigenfunction in B2R and use that by Harnack. It is positive in BR, and you get that if R is big enough. So we have that for sufficiently big enough R, such that this ball is inside the half space. Then, of course, if U is monotone, for U closer to the boundary, U can only be smaller. So you'd have the same bound. Actually, this bound can be proved even without monotonicity. That follows from a result that's going to appear this year of mine. But well, in the presence of monotonicity, we automatically get also bounds, L1 bounds L1 bounds close to the boundary. It's just by monotonicity and by this thing here. And this is sufficient to immediately say that even super solutions do not exist, which are increasing and convex in the normal direction. It's clear, right? Because the function should grow at least linearly in xn, but then these integrals, when x0 is sufficiently far from the boundary, would be as big as you want, and they will not be bounded by a constant. So this already, this observation on L1 bounds, but we are going to use them again later. But they are already sufficient to say that there are no solutions which are convex and increasing in the normal variable, right? So what we are going to try to do now is to prove that if we have a monotone solution, that is a solution such that U of xn is positive, then it has to be convex in xn, and then it should not exist, right? By this result over here. Okay, so let's move to convexity. So what was the idea of Chen-Lin Zhu to prove convexity? It's sort of a surprising, a very nice idea. We are going to look, it's an idea in a sense that comes from ODEs, from dynamical systems. Look at U second over U prime. So look at UXN divided by UXN. UXN is positive, right? So you can do that. And even you can optimize that by adding a weight, which is 1 over xn at infinity, and take that function. Z is going to be this denominator over here, and look at that function and check what it satisfies. Okay, it's a simple computation. The UXN is, as I said, of course, a solution of the linearized equation. And since it's positive, this already means that U is a stable function, stable solution. Then by convexity, UXN is a super solution of the linearized equation, right? If F is convex. That's also. And then this Z here, is a strict sub-solution. And actually, it even satisfies minus this equal to minus 2 UXN xn. So by a direct computation, this function xi is a super solution of a very nice equation of the following thing over here. Minus proportion of z, minus gradient, minus proportion of xi, minus gradient of xi with a vector field, which is the gradient of z over z, is bigger than xi squared in the half space. And nicely too, xi is 0 on the boundary, because xi is UXN xn, and UXN xn is the Laplacian, which is 0 at the boundary, because all tangential derivatives are 0 there by the Dirichlet condition. So we have a super solution of an equation like that, which vanishes on the boundary. And what we actually want to prove is that this xi is a positive function, right? If xi is positive, then UXN xn is positive, and then we are done. So all we have to do here is prove that xi is a positive function, which, when you look from here, is essentially, you may think of this as a maximum principal result. And that's exactly what Chen-Lin Zhu did. So we have our function xi, which every time I'm going to recall what it is, we want to prove it is positive. And it's a super solution of this of an equation like that. Okay, so of course, we don't have a maximum principle just so simply as that, because we are in an unbounded domain. And maximum principles in general do not hold. And what Chen-Lin Zhu observed is that you can prove a maximum principle of fragment Lindelof type This is exactly fragment Lindelof maximum principles in half spaces and more generally cones. Because we can control both the solution, the super solution psi itself, and this the first order term, which is grad z over z at infinity. Because what are psi and grad z over z? Both psi is a second derivative of xn over uxn. I mean derivative of uxn over uxn, and gradient of z over z is exactly the same. Z is the first derivative, so the gradient of z is behaving like the gradient of uxn over uxn. And uxn itself is a solution of a linear equation. And if u is bounded, this linear equation has a coefficient f prime of u, which is uniformly bounded in the half space. So by regularity and Harnack estimates, it is a known procedure, you can get a logarithmic gradient bound for solution of this thing, which is exactly what you need to bound both gradient of z and psi to get bound on the gradient of uxn over uxn. And that's the essence of the proof of the positivity of psi in the work by Chen, Li, and Zhu. And it uses very strongly that u is bounded to have this coefficient f prime of u here being bounded. What we are going to do is we are going to look at this equation in a sort of a different, and that this maximum principle only uses that the right-hand side here is a positive thing, right? We have just psi is a super solution of a linear equation. What we are going to do is we are going to observe that this inequality here can also be written in divergence form with a weight. So actually, this thing over here is written very simply as a super solution of a divergence form operator, however, with a weight, and this weight is z, the function 1 plus xn times uxn. And then we're going to try to use this divergence form inequality and in a sense also use the full strength of the fact that we have a psi square power bigger than 1 on the right hand side. So this is much more than just saying psi square is much more just 0, right? Because it is the super solution itself with the power. Of course, one needs to be careful because the weight here, the z, is a function. It's essentially uxn, and it can be both infinite or close to 0 in the domain. So it's strictly this z is strictly positive. The z is strictly positive, but it can become arbitrarily large or arbitrarily close to 0. This is not a priori a standard elliptic operator, even though it's essentially it's a diffusion, which, however, is not completely controlled. Okay. So there we go. And so what's the idea? The idea is take this thing and try to estimate the negative part of psi. You want to prove the negative part is 0. And try to estimate it by a sort of a quantified iteration of Moser type. If you know the proof of the weak Harnack inequality by Moser, you're going to imagine easily what I mean here, even though I'm going to give a couple of more details. And the point is that in the Moser iteration, in the Moser proof of the weak Harnack inequality, there is an inverse Horden inequality, or LP to LQ inequality for P bigger than Q. And here it comes out thanks to the fact that we have indeed this power here bigger than 1, right? So a few more words on how the proof goes. We're going to back to that. Is we are going to test this inequality. This is usual in the Moser approach by powers of the psi minus and a cutoff, which we are going to scale in such a way that, but after that, we need to optimize the inequality that comes out after the testing by relating the power of the psi and the scaling parameter r. And then we are going to send that power to infinity in the inverse Horden inequality, which will end up in an L infinity bound. And since we optimized and we need some additional bounds that comes for that are viable for stable solutions, the right-hand side of the inequality, see there's the inverse Hölden inequality that tells you some LP norm of psi, which will actually be weighted, is bound by some lower norm in a sense. And actually, to the left, we are going to get the L infinity norm of psi. To the right, we are going to get something that actually goes to 0. So that's how psi minus will have an L infinity norm in the end, which is 0. So it really there's optimization, this sort of an optimization of the Moser iteration with respect to powers and scaling. I'm going to give a couple more details, but that's the idea. And so this thing actually results in precisely a sort of an inequality of Moser type, which I'm going to give here since it definitely is of independent interest, and we're quite sure it's going to be useful in other contexts. So let's assume we have a diffusion operator with some weight which is positive, not bounded, but positive, only L infinity work, and not bounded neither below nor above by positive constants. And we have a super solution of an inequality like that. It's enough even to take psi minus here. Okay, and we have a positive function, Rn plus here, because that's what we're interested in, but that's very valid in any domain, of course. And then for all radii, and all sufficiently large m, which depend only on this q here, bigger than 1, we have the following inequality. So it's a weighted LM estimate on psi minus. And on the right, we have m, where this is the m, over r square. R is the size of the ball where you take the inequality, times some L1 norm of the bounded of the diffusion coefficient itself. Actually, this is much prettier if you write it with respect to the measure given by this, call it, I don't know how, the invariant measure with respect to generated by the diffusion operator. So if the mu is just ADX, then what we are saying here is that psi to q minus 1 in the LM space with respect to that measure mu is bounded by m over r square times the measure itself of an annulus with size r to a power 1 over m. That's what comes after optimizing this inequality after testing with powers and scaled cutoffs. So now see, of course, if when we take m to infinity, the right-hand side goes to 0, we are in business. So we have to check now whether could be lucky enough to have, and we have also the right to take r with respect to m the way we want. Both r and m are free here to be as big as we want. And we can take them one to optimize with respect to the other. Okay, so that's, we have an inequality like that for power bigger than 1, results in a LM norm on every ball. Just the plus here, as probably you guessed already, is half ball centered at the boundary. And such that the LQ norm of the super solution is controlled by something which is only in the form depending on m, on r, and the way this measure measures a ball to a power 1 over m. Okay, so that comes. A few words on how this is proved. Actually, this is you have to do some fine estimation, but the general idea is pretty standard in the Moser theory. Is that you test with some powers of psi times a cutoff, and after computation you get precisely, which you need to do precisely to have all the constants too. You get precisely an inverse Hölder inequality. Here psi is to a power bigger than here. This theta is actually q minus 1. So there's more powers of psi here than on to the right. You pay for that with a gradient of the cutoff corresponding to phi square, but then this cutoff can also be optimized. Then you take powers of our cutoff, that's where m comes in, and you take a rescaled function for the cutoff, and you choose a good alpha with respect to m, and you end up with the inequality which I showed on the previous page, which essentially means m over r. After doing this in the... So to come back to what we cared of, once more this theorem, once more the previous theorem, which tells you this. And the corollary, which essentially what you see from here, this thing here, is that if this measure mu, which is just ADX, and I is the coefficient here, if this measure mu is sub-Gaussian, which means that mu of any ball is smaller than exponential of r square, or in other words, if you don't like measures but just want to look at A, this means that the log of the L1 norm over BR of this A here is a little over r square. Then this thing here has a maximum principle, that is psi needs to be positive if psi satisfies this thing over here. Well, how? You just set m equal to epsilon r square here for each epsilon, and then let epsilon to 0, and and m to infinity. So you take this for each no matter how small epsilon, take m to infinity. This thing goes to the L infinity norm. This thing goes to 0 precisely because of that. This going to 0 is exactly this thing over here. So we have that. Okay, with that, now we only need to check whether the A we had in our inequality, which was the Z, and the Z was what? The Z was 1 plus xn times uxn, the first derivative. So now we have to check if this thing over here is valid for that Z. So here's that again. We have our xi, our z, which is 1 plus xn uxn. We want to show that the xi is positive. And to show that xi is positive, we dispose of the super solution inequality here, minus lxc bigger than 2x squared, where L is this operator, and once more, that's z. So if z is an A, which happens to satisfy the assumption from the previous theorem, which was precisely log of integral over BR of z squared, but that's, in our case, it's bounded, for instance, by log of 1 plus r squared to the gradient of u over any ball BR. If this log happens to be little over r squared, we are finished. Psi is positive, hence uxn xn is positive, hence u is convex, hence u does not exist. Okay. So and this thing here actually comes from estimates for stable solution. This is where stability is going to be used. And let me show you a general result. For a general F, it is included in that paper, which also João quoted a few minutes ago by Cabrefi, Galero, Soto, and Serra, that if we have a positive stable solution of minus proportion of u equal to f of u, then we have a gradient bound in terms only of an L1 bound. So u in H1, that's an interior bound. For a given ball, in the half ball, the gradient is controlled by a constant which depends only on n. And this is what's striking here. This C does not depend at all on f. It's all the same, just an f, any positive f. The stability gives you a uniform constant. And if in addition we have a Dirichlet condition on a boundary, and f is non-decreasing, there's also up to the boundary result. Up to the boundary thing. So this thing here, see, this thing here combines precisely with this thing here. We have a bound on the gradient in terms of in terms of L1 bounds, but we started even our talk with L1 bounds. So it also goes in smoothly. An observation is that for the Lane-Emden equation, or for powers for functions f of u which behaves like powers, which have this hypothesis, which essentially means that they are like powers at infinity, this very hard and deep result is not needed. So it's not like we needed that result to close the proof for the Lane-Emden equation. For the Lane-Emden equation, these bounds are known through a much simpler proof by using the stability if f behaves like a power. But this result closes the question for any f. So, okay, so with that we are done, because we have our inequality, and we know that the gradient is uniformly bounded in any ball of radius 1. You can cover BR with R to the n both of radius 1. So the gradient U square in BR is like R to the n. And then we clear our assumption by extremely largely. We just need, we have here a log of R that needs to be little of R squared. So we have the assumption of that maximum principle result we had before by cleared way easily. So this ends up the proof. And we have that's the proof of the theorem. Since I still have 5 minutes, I'll just show you a few results for the case f is positive. F of 0 is positive, which I said is very different. And essentially there you can cover it very simply. So first of all, if f is, if 0 is positive and f is 0 at some point, then you just can solve the one-dimensional problem through a trivial ODE argument. So you can assume that f is strictly positive, because if it is vanishes somewhere, there is a solution. For strictly positive f's, we had a result with Scott Armstrong a few years ago, which says that if f actually is above 1 over s at infinity, then even super solutions of the inequality does not exist. So f has to decrease in a sense very quickly at infinity. But for such solutions, we can also quantify, we can also qualify the existence through an integral of f from 0 to infinity. So if this integral is finite, then there is a solution. This actually extends this thing over here. And if the integral of f is infinite, then through an argument from that work here with Jorge Garcia-Mellén and Alex Guas, we can show that even super solutions do not exist. So in particular, this certainly covers the case of f convex, but even much more. So that's how we end up with this theorem over here. Right. Once more. And I think that was all I had to say. Thank you very much for being here and for listening.
Thank you, Boyan, for the very nice talk. Questions or comments to Boyan?
I do have a question. Hi, Boyan. Nice
hey,
talk.
hey, Noemi. Thank you.
You said, and I agree, that the simplest unbounded domain after a Rn is the half space, but also the complement of a ball, let's say.
Yeah, you're right. That's a very different problem. Of course, it's actually from the problem, even from the theory of nonlinear elliptic PDEs as we know it, a complement of a ball is a simpler domain than the half space, because in a sense, having a bounded boundary is a nice thing. But that's a different problem. I mean, I cannot.
Do you have any idea?
Sorry, there you can look at radial solutions, which is also very. I mean, if you take an outside exterior of a ball, you can essentially think of radial solutions. So you have ODE to solve.
What for the existence, but for the non-existence?
Well, actually, it depends. I mean, if you have a boundary condition, if you have Dirichlet at infinity, for instance, yeah, you have radial solutions only. But for non-existence, I'm not sure. I don't know exactly how things. We definitely use that we are in a half space. See that the disk psi function is 0 on the boundary because the boundary is flat.
Mm-hmm. Okay.
Yeah.
More questions or comments? I have a question. Is there a fully nonlinear version for those results? These results? No.
Not to my knowledge.
What's the difficulties in this case?
No, it depends what you mean, of course. For bounded solutions, they are definitely fully nonlinear versions. And actually, one fully nonlinear version is you can find, even though there's been even generalizations, but in that paper, for instance.
Okay.
Then bounded solutions on the dancer type result is obtained. But in general, just like these sort of things, no. For instance, the result for P up to infinity is not known, even for bounded.
Okay, thank you, Boyan. If no more questions, let's thank Boyan again.
Thank you very much.